Hi, this is complex analysis, holomorphic functions, 7th session. This is actually a re-recording because yesterday itself I tried, something went wrong, some technical fault. Yeah, so I am re-recording. So let us go ahead and share that screen. So the first thing you should notice, or let I not share the screen. The first thing you should notice, this is the third. Okay, 3rd June. Okay, let me at least say what we are going to do. Today we are going to talk about analytic functions, define analytic functions, and say what is the relation between holomorphic functions and analytic functions on an open set. Then we will say what lies ahead of the course, that is next series of lectures, what will it deal with. Okay, so maybe I should start afresh. Okay, yeah, so this is 3rd June. So your function f from U an open set C to C is analytic on U, of course, if for every A in U, okay, f admits a power series representation on an open disk BR contained in U. Okay, so this I will explain what this means. But those of you who had already seen my power series lectures will know I have a power series. If it is convergent on a disk, then it defines a function. Then I say the function is represented by the power series, right? So what does it mean? So this means for every A in U, there exists constant Cn which may depend upon A in C, so that and are positive, so that BAR is contained in U, and 2 f of z is summation Cn z minus a to the power n running from 0 to infinity. This should be true for every b z in BAR, right? You follow that? Yeah. So first let us make an observation. If f is analytic on U, then f is holomorphic on U. Why? Because if it's holomorphic on U, what I have to do? Start with any A in U, I have to say f is differentiable at A. Yeah, but around A I know f of z is of the form summation Cn z minus a to the power n from running to 0 to infinity for all z in BAR, right? And we know this function, this power series is infinitely differentiable, and in particular differentiable, okay, at each and every z in BAR, in particular at A. Therefore this is clear. Okay, so pause, review, proceed. So this is the first observation. Second observation, okay, suppose again we have seen this, okay, this is not second observation. The main result of Cauchy's theory is the following: f is holomorphic on U if only if it is analytic on U. See, when we say f is holomorphic, what do we mean? f is differentiable at each and every point of the domain. But if it is analytic, you see that uh, for each point there is a disk on which the function is represented by a power series. That power series converges on the open disk. Therefore, we know it is infinitely differentiable. Therefore, as a corollary, we see that any holomorphic function is infinitely differentiable. Do you get that? Yeah? Yeah. So once you are okay, just make sure you understand what this is. So the mystery why complex differential functions are infinitely differentiable is completely cleared. It is demystified because any holomorphic function on an open set is locally a power series, and we know any power series is infinitely differentiable on the disk of convergence. That's it. Okay, so observation 2 is this. Suppose f is analytic, okay, and a belong to u on u, okay, then we have an r positive, etc. F of z is summation cn z minus a to the power n 0 to infinity for all z in BAR, right? But any power series function on its disk of convergence is infinitely differentiable, and then hence we also know the cn's have intimate relation to the derivative. So we know this, right? Now therefore f of z, suppose I write it like that, what does it really mean? So f is a C infinity function, that is infinitely differentiable function. Therefore I can form it's a Taylor series. Okay. So Taylor series converges and it is equal to the function. You see that it rarely happens in real analysis. Yeah, if you have gone through my lectures on real analysis, differentiation, etc., where I talk about Taylor's theorem, I say in Taylor's theorem there are two problems. Even in power series I come to that. If f is a infinitely differentiable function, then I can form the Taylor series. There are a lot of problems. The function f, okay, may be defined on an interval j, and the Taylor series, okay, is there. What are the possibilities for the Taylor series? It may converge only at that point, not even in the interval. And second, it may converge, okay, on a smaller interval, okay, whereas the function domain is larger interval. Third thing, even if it converges, it defines a function. That function may not coincide with the given function f. These are the main problems. Okay, please understand. If you, the only way to appreciate these things is compare, find the analogies, contrast, learn these things. Okay, so if necessary, go back to my lectures on Taylor series and power series where I talk about Taylor series. So in analytic function, what have you found is, okay, the Taylor's any analytic function is smooth, that is C infinity or infinitely differentiable. Therefore I can form its Taylor series, and the Taylor series converges in an open disk around that point. Okay, are you following? If it converges to the function, therefore f is analytic. Therefore f is analytic if and only if it should be infinitely differentiable, and I have it's a Taylor series is convergent on an open interval or open disk around that point, and it converges to the given function. This is a way of looking at analytic functions, slightly different way. Okay, please pause, run this video again, watch it. Okay, these are the subtle points when usually people do not explain, so you may have problem. So please go through that. So it's now time for us to give some examples. Okay, there is an obvious thing question you will ask, but I will come back to it later. Let us start with a simple example. Right, now let us say f of z equal to z power n, a natural number. Okay, I say F is analytic on C. So how do I prove that? So if you give me an A in C, then I have to write F of Z as some summation Cn. Okay, C. This is okay. Let us write it C n Cn Z minus A to the power n running from 0 to infinity. I have to write it, okay, for Z in some VAR, which is contained in C, right? But what is the obvious thing? Again, if you had understood, if you have gone through my lectures on Taylor series, the first example I talk about is the Taylor expansion. The obvious thing is Z power n, I can write as Z minus A plus A whole power n and apply binomial theorem. Yeah. So what do I get? I am going to get summation, okay, n choose r Z minus A to the power r and A to the power n minus r, 0 to n. Yeah, do you follow that? So therefore I have written it as a, therefore this is going to be 0 to n and Cr Z minus A to the power r, where Cr is n choose r A to the power n minus r for 0 less than or equal to r less than or equal to n and equal to 0 if r is greater than infinity. Therefore I can actually write it as infinity. Yeah, therefore any f, okay, f of z is f of z equal to z power n is analytic. Okay, pause, review, proceed. And what is the Taylor series for this? Remember, Taylor series is going to be f dash of r at A is what I have to look at. So f dash of r at z is going to be n into n minus 1 into n minus r plus 1, right, into z power n minus r, right. This is nothing other than, you can choose, this is nothing other than, therefore f dash at A, f derivative of f at A will be, this is nothing other than n choose r into A power n minus r. So you got it. Yeah, this is just cross verification. Next, if f and g are analytic, then f plus g is analytic. This is very easy. Why? If f of z equal to c and z minus a to the power n 0 to infinity for z in, let us say, BAR1, and g of z equal to dn z minus a to the power n 0 to infinity for z in BAR2, then take the minimum of R1 and R2, then f plus g of z, using the theory of convergence infinite series we are using. It's not pure algebraic manipulation of symbols. Okay, this I had explained many times, so I will not do that, into z minus a to the power n 0 to infinity for all z in BA, right. Therefore, as a corollary, and of course, if lambda is a scalar, f is analytic, then lambda f is analytic. So as a conclusion, any polynomial analytic. Okay, what is a polynomial? Polynomial is of the form c0 plus c1z plus cn z power n. Then I should be able to write in powers of a. What do? You write everything power of z, z power r, z minus a plus a power r, and apply that. Okay, right. So pause, review, proceed. Okay, so now let's look at the second example. So let u be my c star, f of z equal to 1 by z, right? Then I claim this is an analytic. So fix an a in c star. So what do you think I will do? Okay, you had already seen how I managed in polynomial, so the same trick I should do. What do you think I will do? Yes, so I will write as 1 by z as 1 by z minus a plus a, right? But this I can write as a into 1 plus z minus a by a, right? So what do you think I should do now? The moment you see 1 plus x, what is the 1 upon 1 plus x? What should you think? You should think of a geometric series, right? Therefore this is going to be 1 by a summation. So 1 by 1 plus x, what is the geometric series? This converges mod x is less than 1, right? Therefore that is going to be minus 1 to the power n minus 1 by z minus a power n by a power n, and n is running from, sorry, it's n 0 to infinity, because this is a 1 by minus x, right? Therefore minus x to the power n. So this is correct. Do you understand why I got this? Okay. See, I don't remember these things, so at every time just try to work out. You have confidence that you can do it. That's what I did now. Okay, is it all right? Therefore this is nothing other than 0 to infinity of minus 1 to the power n by a to the power n plus 1 into z minus a to the power n. Okay, and when this is valid, if mod z minus a by mod a is less than 1, that is mod z minus a is less than mod a. Okay, this power series expansion is valid in B a mod a. Now let us look at the picture. You should be convinced why this is true. Suppose this is my a. What I can do? Look at this distance. Okay, this is the distance I can go through. Okay, this is mod a. So G, of course, is open. Therefore, 0 will be avoided. The whole thing will be in C star. This is the and also notice that this is the maximum ball of maximal radius R, such that BAR is completely contained in C star. Do you appreciate that? Yes. So maximum possible disk centered at A, which is contained in C star, is this, and on that there is a power series expansion. Next, I would like to check. Therefore, what are my CNs? CNs are minus 1 to the power n by a to the power n plus 1. But is it n factorial? Yeah, right. Right. So what is that? So what is f dash of z? F dash of z is minus 1 by z squared, that is minus z to the power minus 2. Therefore f dash of a is minus a squared. I hope I am doing everything properly. If I am doing some mistake, please make sure you follow that. Yeah. And what is f double dash of z? That is going to be minus 2 into minus 2, that is going to be plus 2 into z to the power minus 3. Therefore f double dash of a is minus a cube, right, into 2. There is a 2, sorry, 2 I forgot. Okay, let us assume fn of a therefore is going to be nth derivative, meaning minus 1 to the power n, and see n. So if you want, let us do f triple dash of a, that is going to be minus 3 into 2 into z to the power minus 4. Therefore minus 1 to the power 3 into 3 factorial into z to the power minus 4. Therefore f triple dash of a is going to be minus 1 to the power 3, and 3 factorial z to the power a to the power minus 4, right? Therefore by induction fn of a is going to be minus 1 to the power n factorial a to the power minus n plus 1, right? Therefore this is going to be minus 1 to the power n factorial a to the power n plus 1. Therefore this divided by n factorial is going to be minus 1 to the power n a to the power n plus 1. That is your Cn. Yeah, this is just to get us confused, get us convinced what we are doing is correct. Yeah, so pause, review, proceed. So the third example is, let us do f of z equal to exponential of z, which is e power z, okay, for z and c, right? So fix an a, now fix a in c, then what do I want? I want, this is going to be, let us z power n by n factorial 0 to infinity. So immediately you can try to do the same trick, z minus a plus a to the power n by n factorial, right? But this one is okay, but there is a much smarter way. Let's look at e power z or exponential of z, if you want, is e power z minus a plus a, right? This is e power a into e power z minus a, therefore it is e power a into summation z minus a to the power n by n factorial 0 to infinity. Is it? This is much cheaper. Yeah, do you like this? Now again, if you want, you can just check various other things. What is f dash of a, okay, e power, that is f dash of z at z equal to a, that is e power z at z equal to a, therefore it is e power a, right? And what is f double dash of a? Again it is the same thing, f dash of z is e power z, therefore it is e power a, right? Therefore we any nth derivative of this is e power a, right? Therefore what should be the Taylor expansion? Nth derivative of a by n factorial into z minus a to the power n. Okay, this is e power a by n factorial into z minus a to the power n. Therefore it's e power a into 1 by n factorial z minus a to the power n. Yeah, therefore if I write f of z as summation c n z minus a to the power n, what are my cn's? Cn's are nothing other than e power a by n factorial, which is nothing other than, so again we verified. Okay, pause, review, proceed. So the fourth example, I will leave it as an exercise. You have cos z, right? Again you have a power series expansion for cos z, okay, and I want to know whether f of z equal to cos z is analytic. As similarly g of z equal to sin z, z in c, is it analytic, right? So you can have the power series and try to do, but a smarter way will be write z as z minus a plus a, therefore you apply the addition formula equal to something in terms of cos and sine. For cos and sine, now remember a is constant, only it will be powers of z minus a, right? So this I leave it as an exercise. Find the power series expansion in terms of z minus a. This is not exponential expansion in terms of powers of z minus a. Okay, that's an exercise. Now let's come to the first thing. Many of you would have lost the thing. Suppose f of z is a power series function, namely Cn z power n. For simplicity, I am assuming it's a power series function defined on a disk centered at 0. Whatever I am going to say, it could be z minus a also. Okay, the same thing. It could be like this, z minus a to the power n. This may be the power series which is defined on BAR. Then I want to know is f analytic on B0, or in this case I will ask, is it on BAR? So what does this mean? This means give me any a in B0R, I should be able to find coefficients dn, so that is dn z minus a to the power n, yeah, for z in some domain BAR containing B0R. Here what should I do? For every b in BAR, I should be able to write it bz z minus b to the power n, and okay, z now belong to b small r, which is contained in BAR. Okay, so I am going to concentrate only on this. Focus on f of z equal to Cn z power n 0 to infinity, where z is in B0R, where r, of course, r is positive, maybe infinity. Okay, so as we did polynomial, the natural impulse see, remember when we had exponential function or cos function, okay, we use the property of the function rather than something to do with the power series directly to get the desired power series expansion in terms of z minus a. Please follow. Don't be mesmerized by my words, by my sentence. When we had looked at e power z, exponential z, okay, that is given as a power series. When we wanted to prove the function exponential functions are analytic, I did not look at the power series part. I looked at only the properties enjoyed by exponential. Exponential z equal to exponential z minus a plus a, therefore it's the exponential a times exponential z minus a, and therefore I get the power series expansion in powers of z minus a. Similarly for cos and sine, if you have done that. Are you following? Whereas here I only, in fact my function here is completely defined only in terms of powers only. Therefore the natural impulse may be try to do something like Cn z minus a plus a to the power n 0 to infinity, right? Try to, okay, manipulate and try to see whether you can get it. So this is what, so z minus a plus a, this z power n equal to this is equal to summation n choose r z minus a to the power r and a to the power n minus r, where r is 0 to n, right? Therefore I can write f of z equal to summation n equal to 0 to infinity and summation r equal to 0 to n. Okay, there is a Cn here, n choose r, z minus a to the power r, a to the power n minus r. So I got something in which z minus a to the power r comes, but what is that I want? I want to write it as summation dn z minus a to the power n. Therefore I should know, or if you want, dr z to the power n minus r equal to 0 to infinity. You follow that? Okay, so here there is a thing, so let me just put a symbol, right? Right, so I want z minus a to the power r come. So this is interchanging summation. Okay, that is Notice that if it's a finite sum, you can always do that, because when n varies, here also the n varies. Please try to understand. If I know something like this, ai, okay, and something here bj, j equal to 1 to n, where n is fixed at I equal to something 0 to infinity, then I know it's very easy for me to do. Are you following? Because this is going to be 0 to infinity of a bj and j equal to 1 to n, therefore I can take it out. Okay, because bj is common, therefore it's going to be something. This is going to be summation bj and I equal to 0 to infinity of a. This is j equal to 1 to n. Are you following? This is what we have seen, convergent power series. Yeah, suppose summation a 0 to infinity is convergent, therefore bj times summation a is convergent, again I equal to 0 to infinity, j running from 1 to n, therefore okay, summation b1 ai plus summation b2 ai plus summation bn ai, this is convergent, right? But this is nothing other than b1 times summation ai, this summation b2 times summation ai, etc., plus bn times summation ai. Okay, now remember, since it's convergent, these are all okay. Summation bi, suppose I call it as beta, this is b1 beta plus b2 beta plus bn beta, therefore it's b1 plus b2 plus bn times beta. So all those things I know. You follow that? So if it is finite, it's okay, but then this n keeps varying. Here it also varies, so you have to interchange the summation. Okay, this is usually known as double series. I will explain what is involved, okay, and I will refer to another video of mine which will be recorded and released soon. So what is happening is the following picture. Keep the following picture. This is how it is. Okay, now so let us assume this is R side. So okay, this is nn, okay, or if you want to say r, this is r, this is equal to nn. Yeah, then what we are doing is, okay, when I am fixing an n, I am running r from 0 to, this is r direction, this is n direction, therefore r equal to 0, r equal to 1, r equal to 2, r equal to n, and different n I am going like this. Okay, this is another n, then n equal to 0, n equal to 1, sorry, r equal to 0, r equal to 1, r equal to 2, r equal to capital N minus 1, r equal to capital N. Do you understand? This is how I am summing. I am summing. Okay, this one you can think of this Cn summation. Okay, whatever I used. Okay, this summation is what I am doing, row wise first, then column wise. Now what I want to do is, I want to do it the other way around. I want to do it, okay, suppose I have fixed an R here, then I am going to run across. See, so this, the picture is not good, all those things should be the same place. Let us see that. Okay, this is R. Okay, my n runs from n equal to r plus 1, r plus 2 to infinity, because my n can run up to infinity. Do you understand this? Yeah, therefore this fellow is going to be whatever I wrote, Cn n equal to 0 to infinity of summation r equal to 0 to n choose r, a to the power n minus r, z minus a to the power r, this is equal to, okay, r equal to 0 to infinity and my n equal to r to infinity of this. Okay, now n is the one which I am choosing, therefore it is Cn, n choose r, a to the power n minus r. Now you do this, z minus a to the power r. So this is your dn. This is formal. Why it is formal? As I said, we are using a double series of this form. Okay, aij and sum it over j and sum it over I. Suppose aij, maybe I will make the point clear. So let us look at the summation. As I said, okay, this is the one. Maybe no, I will. Sorry, I will write in this slightly different way. Suppose a11, a12, a13, a1n. Okay, I am summing this. Okay, a11, then a11 plus a12 plus a12 like that. You understand this, and then this, and these are the partial sums. Okay, so the series I get is a1j. Right. So now I take ai1, ai2, ai3, ain. When I submit the series, what do I get? aij. And this is joining j equal to 0 to infinity or 1 to infinity. I don't care what it is. Maybe I wrote as 1, so let me write 1 to infinity. Now I can sum the other way around. This I can sum along this way. Here I can sum a11 plus a21 plus ai etc. plus ai1 and so on. Right? Therefore, what I get is summation. I get here a. Okay. What is I1 I equal to 1 to infinity. Here I will get, second one will be I will get a I2 I equal to 1 to infinity, and here I will get a I n I equal to 1 to infinity. Right? You follow that? Now let us call this as alpha 1, alpha 2 etc. alpha n. Here when I compute, let me call this beta 1. This is my beta 1. This is my beta 2, beta 3. So when I am summing like this, okay, this is my alpha I. When I am summing like this, this is my beta I. This is my ith element. Okay. So what is that I want? What is that I want is that summation alpha. Now what did I get? I am getting alpha I, right? Summation alpha I equal to 1 to infinity is equal to summation beta j equal to 1 to infinity. Expand this. What is I equal to 1 to infinity? Alpha I is j equal to 1 to infinity. This is summation j equal to 1 to infinity of beta j. That means ij. Now I am running from I equal to 1 to infinity. Are they equal? This is the problem. So I am simply interchanging the way I sum. Either I sum the thing infinite series via row wise first, and then the sums will be at the end, so column wise, or I take the double series, sum it along column wise, then I have bottom thing will be my summations beta 1, beta 2, beta n, and sum it row wise, whether they are the same. This needs proof. Okay, we have to make assumptions so that this is true under certain assumption, under additional hypothesis. Okay, right? So this is a version of Fubini-Tonelli theorem for n with counting measure. Okay, That means I have n and take this, use the product measure, product counting measure. If you apply this, these are all some kind of jargon to frighten you. Okay, don't get frightened, don't worry about it. Okay, this can be proved in an elementary way. Okay, this will be topic of one separate video. I don't want to do that. Now come back. So what we want to show is, so I have this series, whether this is true. Okay, and we can justify. Okay, can be justified. So assume this can be justified. Whatever the additional hypothesis I have to assume for the double series thing will be valid here. Therefore it becomes, I can interchange the sum. Therefore I have shown that any function which is defined by a convergent power series is actually analytic on the disk of convergence. Okay, if you don't want any of these things, simply assume. But what you should know, just because it's a power series, you cannot immediately conclude it is an analytic function. Why? What is the subtle point? When I give a power series, it may be of the form Cn z minus a to the power n, but when I want to show it's analytic for any b in the disk of convergence, I have to write it as summation dn z minus b to the power n. So I have to find such an expression, okay, dn's, and show that this converges to my function f. That is the subtle point. Okay, because I have seen some people saying power series function is analytic. It is obvious. It's not obvious. Analytic functions as be defined. Yeah, and notice that if my power series is actually a polynomial, this we had already seen. In fact, we used it. Okay, here R is actually infinity. Okay, this we had already proved earlier. This is analytic. Okay, by rigorously. So we have defined an analytic function. We gave some non-trivial examples. We also showed, okay, assuming certain fact from W series that any power series function is also analytic on its disk of convergence. But remember, the reason why I introduced analytic function is to tell you to take one mystery out of complex analysis. Why? Once a differentiable complex function is infinitely differentiable, because each holomorphic function is analytic. That means each holomorphic function is locally a power series, and a power series is infinitely differentiable. This is going to be a lot of work for us. In the next series of lectures, we will develop methods and tricks to prove this. Okay, stay tuned. We will meet again.